So I'm not supposed to assign work during dead week, during week 15. But if you would like more time, I feel like it's okay to grant extensions until the last day of the semester, which would be the 21st. So. Okay, so if you want to go back to any homework, you can work on it until the 21st. And then here's the side note. Oh yeah. So I had a question from homework 7.6. So at first I thought, okay, let's add some extra time, which I did. I put homework 7.6 due on Sunday. Okay. Then I went to do the problem. And of course, I was warned that it was a messy problem and started to do this integral and break up the integral, and then took one piece and did that piece by parts. And then one of those parts made me go to Google, and then I was on Google and first checked Wolfram Alpha, which the answer looked kind of crazy, and then checked just with some other people's work. And I'm going to go with what someone said right here. What did they say? They said, you can use integration by parts, something, something, something. The latter integral, which I'll put up on the board, is calculated by using clever, complex analytic techniques, which I don't expect you to do. So I'm going to see how to give you credit for that problem, or maybe I'll just add a little extra credit to this overall score to just make up for making you do this problem that we can't really do. So I'll figure out how to fix that. I was going to work through the problem, but we can't really do a particular part. I'm going to tell you what that part is. So this was from 7.6, number 5. I'll show you like some of my scratch work, but then we get stuck. And I kind of remember my Calc 3 teacher explaining this. We'll get there. Okay, so the integral looks like negative infinity up to infinity. There's an x squared, and e and negative x squared dx. Before I erase, I feel like this is going to be the end of the homework. If I make any more homework, it will just be for practice or extra credit. We'll talk about it later. So this, we split up. We go from negative infinity to 0. And then go from 0 to infinity. Okay, and I took just one part, just the stuff on the right. Okay. And then first I'll write what the limit would look like, and then we'll check out what the indefinite integral looks like. Okay, this. The limit as t goes to positive infinity of the integral from 0 up to t of your function. And then I didn't even worry about evaluating the integral. It just this indefinite integral for x squared. Okay, that, I tried integration by parts. And that will be -1/2 x e to the -x squared evaluate. Well, I don't even have to evaluate. I'm going to take away that part. Okay, subtract. I'm sorry, add. 1/2. Then there's an integral. I don't need those parts. E to the -x squared dx. Okay, this piece here I've seen before. I think it was like at the beginning of Calc 3 where my teacher kind of introduced integrals that we can't easily evaluate. And kind of let me check this out on the side. And then we need to get back to actual class notes. Okay, so if we tried to doing that one, which I'm just going to throw into Wolfram Alpha integrate. Just e to the -x squared. And it says root pi over 2, and then it says root pi over 2. Okay. But let's see. Let me go see. I have my old notes, so let me go see what my teacher told me about this. I'll be right back. Never mind about that. I'm just going to go back to what this other person said on Google, which was that it's a value which is found using clever, complex analytic techniques. So I'm not quite sure how to get that. I could do some more Googling later, but for now, let's go back to section 9.3. And this is kind of easy stuff. We're talking about functions, which we've been working with all semester. We're just adding an extra variable. So 9.3 is functions of 3 variables. I guess it's functions of several variables, but we're going to have x, y, and z. Let's start here. Definition. Let f be a function. With domain, with domain D. The domain is a set of ordered pairs. We're going to draw a picture soon. Right now we've got is a set of pairs. Ordered pairs where first is X and then Y. Okay. Okay, each of these ordered pairs needs to correspond to a value C. Let's do this. It's supposed to say, I can rewrite it, corresponds. I'm just thinking in my brain, every function means if there's an input, it has one output. We're inputting a pair, but you still output, they're still going to one output. So the book says every pair has a unique, corresponds to a unique real number f of xy, or we're going to call that c. But I think I want to say to like, it means the same thing, to exactly one real number. Okay, so our function is called f, and it has domain D. In that set D are ordered pairs x and y. Every x, y gets sent through the function to only one output, one real number called z, which is f of, the book says just xy, but I like to put in the actual pair. So f of the pair, xy. Okay, I think that's it. And then f is called a function of x and y. D is the domain of f. The function maps to a codomain, which we're going to draw. And the set of all of your z values, all of your f of x, y's, is the range of your function. Okay, let's draw. Okay. D is a set of ordered pairs x and y. So in this set, on this side, okay, let's do something like x1, y1, and x2, y2, so on. Then your function, f, sends every input to one output. You input x, y, you output z. Okay, so the codomain is going to be the set of real numbers in our class. We work with real numbers. The outputs for your function are a subset of the real numbers, and they're called the range. So in here, let's do this. codomain going into the range, which is a subset. Cool. Like Z1. Like say f takes x1, y1 to z1. It takes x2, y2 to z2. And just a reminder, again, every input has only one output. So let's give it a try. Let's try a function f of xy. We have 5x squared minus 2y squared. Let's find input 3 pairs. So A, B, C. Okay, we're going to put in 2, 0. 2 for x, 0 for y. Let's put 1, 1. And we're going to put in -2, -2. So first we're going to just do the scratch work, and then I'd like to also draw a picture. Okay, x equals 2. Again, this is how the book writes it, but I would think that you're putting into your function the full pair. So I would write it like f of the pair 2, 0. Okay, 5 by 2 squared. Subtract 2 times 0 squared. Which is going to be 0. 5 times 4 will be 20. Let's just put it on the side. Okay. Let's do part B. Put in 1, 1. Five times 1 squared, subtract 2 times 1 squared. So 5 minus 2 is 3. And also, please look for mistakes or, typos, stuff like that. All right, let's put in, so it's not very clear which one is x or which one is y. Let's make this -3, so that way it looks more fun. Okay, -2 for x, -3 for y. So whether you use 2 parentheses or just 1 pair of parentheses, it's the same idea. We put 5 times -2 and then squared. -2 times -3, just gets squared. 5 times another 4. Yeah, minus, because we're going to have +9 here, and times 2. I got 2. So we're going to go from the domain to the range, just straight into our set of outputs. What was the first one we did? It was 2, 0. Okay, we put in 2, 0, 1, 1, -2, -3. Our function, f, took 2, 0 and sent it out to the real numbers to the number 20. Okay, when we put in 1, 1, f takes that input and sends it to an output of 3. Okay, and then we also say it like f maps this input to the output 2. Okay, so the whole huge set is supposed to be the real numbers, and the subset where your function is sending outputs to is the range. It's not going to fit. Okay. I guess the only thought I'm having is that the difference between the domain and the difference between the graph. So the domain is all of the pairs of inputs, and the graph is the, let's just write it down. Okay. Okay, so the domain we're going to call D. D equals the set of all x, y, such that f of x, y equals Z. Just all the pairs that are sent to some output. Okay, and then the graph. This is all your x's and y's and z's. Such that, how do we say? Let me see. What would the book say? I guess such that, let me see. Okay, the graph is the function of the surface in space where we have x, y, z, z equals f of x, y. We already wrote that right there. The domain. The domain of the function is a two-dimensional set that consists of points in the xy plane. Well, I feel like I'm repeating myself, but all I can think of to put here is such that we're talking about the graph of a function. So we do have a function f. I'm just going to write the same thing. Just trying to point out that the domain is a set of pairs and the graph is a set of triplets. Moving on. Okay, let f of x equal oh, f of xy, two variables now. The square root I'm going to use this problem. Square root of 64 minus x squared minus y squared. Oh, and I have a question. Find the domain and the range. So the requirement is that your function maps from the real numbers and the outputs are also going to be in the real numbers. So just like, where can I make this fit? Your function starts from the reals, goes over into the reals. So if we send in xy, we want it to go to some z, and z has to be a real number. So if you take the square root of a negative number, it becomes imaginary. Like the square root of -1 is I. So we need the expression under the square root to be a positive number. Yeah, if it's equal to 0, then you've got a square root of 0, which is 0. If it's anything positive, then we're taking a square root of a positive number, which is a real number. But then again, like I said, if this expression is negative, the square root of a negative number is imaginary. It is a square root, okay, well, an even root, but still. Okay, let's go on and just work on this part. So we have 64 minus x squared minus y squared greater than or equal to 0. We're going to add x squared and y squared to the other side of the inequality. Okay, scratch work for finding the domain is going to have 64 greater than or equal to x squared plus y squared. Okay, so the equation of a circle. So let's see what this is. Domain, that's the domain. So the domain is the set of all points that lie on or inside this circle that has a radius of the root of 64, which would be 8. Let's write this down. The domain is the set of all xy. such that x squared plus y squared is less than or equal to 64. And I think then we can find the range. So let's go for the smallest value and the largest value. The smallest value we can have is a 0 for x and a 0 for y. 0. And then let's go out to that largest circle, which I said was the radius of 8. Let's see. Diminish the set of all points that lie in or inside the circle by on or inside. Okay, now let's work on the range. Think about I'm trying to write this first. Let me use this. Set of z values such that z is between 0 and 8. I think that's good. Okay, and then we're going to also draw a picture. Okay, we're on the x, y axis. We're drawing a circle of radius 8. So let's go this way for x and this way for x. Positive 8, negative 8. Positive 8 for y, negative 8 for y. And then trying to do my best to draw this. Okay. And then the range is your possible values of z. So from 0 up to, let's say, that value is 8. So what we have is a hemisphere, the top of just the top half of a circle. It's kind of okay. And then we have stealing this example from the book. So we've labeled it the hemisphere, where f of x, okay, is the function we have. F of xy equal to And this part is just that circle right there. The whole function is giving you this half dome or this hemisphere that's above that XY axis. Okay, let's see. We have 10 minutes, so I think I want to just try one more from the list of homework problems. And let's get the domain and range. Okay, let's do this one. We've got ln of x plus y. A little iffy about it though. Just give it a try. Let's just try it out. And then that'll be it for today. So for half of xy is ln of x plus y. The domain. And range. Okay, I know I can go do the domain part. It's the range part where I might need your help. Okay, domain. So ln of something. Let's say ln of t. I know. Looks like this. There's this asymptote here where your t values cannot be less than or equal to 0. Like you're never going to reach 0 here. There's no value of, or like the value t equals 0 does not have an output for ln of 0. Okay. Ours is ln of x plus y. So we need x plus y to be strictly greater than 0. Like on this one here, this is has t greater than 0. Okay, so let's see. Maybe I could just put y greater than x, which we could graph. Okay, let's do x's and y's. And let's put down first the line y equals x in dots. Already thinking to myself, I'm going to play with this problem and we'll talk about the range next time. But as far as domain goes, I have the set, so we would write d is equal to the set of x's and y's such that y is greater than x. And over here, we're trying to draw that. So let's test something. Let's test a point like over 2 for x, 0 for y. So that's for my sketch here, I've already got an answer for the domain. But for my picture, I'm trying to test 2, 0 in y greater than x. That's my x. That's my y. So is 0 greater than 2? No. 0 greater than 2 is false. So this is not in the solution set. The other side of the line is part of my solution set. So that is all values where y is greater than x. And all of the points in this, it'd be a plane, are the domain. I think it would be a plane. Okay, that's good for today. We'll come back next time and talk about the range of this one. And yeah, let me know if you have any homework questions. I'm sorry that I assigned a homework question that was kind of like not possible to do. Right. Anyway, bye everybody. Have a good day. Thank you for coming to class.